Hello, I welcome you all to our own channel MSK Learning. Now in this video we will see the Bernoulli's equations. As you know, the Bernoulli's equation is basically derived from the Euler's equations, right? So the Bernoulli's equation is basically it is the equation in which the fluid flow in a fluid flow the sum of all the energy is constant, and basically we have a three type of energy head we have to counter, that is the pressure head, kinetic head, and the potential head. So the Bernoulli's equation on this screen, that is statement: Bernoulli's equation is obtained by integrating the Euler's equation of motion. So whatever the Euler's equation we have in fluid mechanics, once we integrate the Euler's equation, we will get the Bernoulli's equation. So the Euler's equation is nothing but dp by rho plus z dz plus v dv. This is the pressure head, this is the kinetic head, potential head, and this is the kinetic head. So once we have to integrate this dp by rho and g dz plus v dv is equal to constant, we'll get the Bernoulli's equation. So let's say that we have a flow is incompressible. Incompressible means the density is not changes, it is going to be constant, right? So while on integration, that the above equation will yield this, that is p by rho plus zz plus v squared by 2 is equal to constant. Further, that on simplification you can say that let's take the z as a common, so p by rho g plus z is equal to v squared by 2g is equal to constant. All right, so this is the equation of the Bernoulli's equation, that p by rho g plus v squared by 2g plus z is equal to constant, right? Where the p by rho g is nothing but the pressure head, v squared by 2g is the kinetic head, and the z is the potential head. So here we can say the p by rho g is the pressure energy per unit weight of the fluid, or pressure head we can say. V squared by 2g is nothing but the kinetic energy per unit weight, or kinetic head, and the z is the potential energy per unit weight, or potential head. All right, so now while you have to derive the Bernoulli's equation, you need to take some assumption, right? That what type of fluid flow and all those things. So there are the four assumptions basically. The fluid is ideal. Ideal means it don't have any losses, or you can say the viscosity is zero, right? The flow is steady, means the properties of the fluid does not changes with respect to the time, it is going to be constant, right? The flow is incompressible. Just now I told you that flow is incompressible means densities remain constant, and the flow is irrotational means it won't rotate about their own axis, right? So now these are the four assumptions you have to take while analyzing the Bernoulli's equation. So based on that, we will see that how to apply the practical applications for the Bernoulli's equation with the help of one numerical problems. Let's see that. The problem on the screen, please read it and write on. So one problem on the screen, you can see that a pipe through which water is flowing having a diameter of 20 centimeter and 10 centimeter at the cross section 1 and 2. The velocity of water at section 1 is 4 meter per second. Find the velocity head at section 1 and 2 and the rate of discharge, right? So one pipe is there that having two section 1 and 2, that having the diameter is given at 20 and 10 centimeter, as well as the velocity is given at one of the section, that 4 meter per second. We have to find out the velocity head at all the section, means at both the section 1 and 2, velocity head in the sense that v squared by 2g, and the discharge. All right, so first of all, we don't have a what we call that velocity at the section 2. So for finding the velocity at section 2, what we will do, we'll simply apply the continuity equations. All right, so we will draw one schematic layout of this problem, and then we try to understand this question. So the problem on that solution we had here, we have a solution that one pipe we will make of having varying cross section like this, and it is like this, right? So let's say this is the section 1, all right, and this is the section 2. Okay, so just for the convenient, you can draw the schematic layout. At section 1, the diameter is, let's say it is the d1 is equal to 20 centimeter, all right, and the v1 is equal to 4 meter per sec. Okay, then at the section 2, that is d2 is equal to 10 centimeter, it is given. We have to find out the v2 is equal to what. All right. Now, so first of all, what we do, we have to find out the v2, right? And then let's here that is, you can say a1 is equal to pi by 4 into d1 is square. That's capital I have written here, I'm written the small. There's no problem, you can follow anyone, right? So pi by 4 into, let's convert this into 20 centimeter, means that is 0.2 square. All right, so you'll get the area that a1 is equal to we have the 0.0314 meter square. Okay, now similarly you can find out the a2 also, that is a2 is nothing but which is pi by 4 into d2 is square, means 0.1 whole square. All right, right. So this area is nothing but you have a here only we can write 0.00785, okay, meter square. So the 0.00785 meter square is the area at 2. Now first of all you have to find out the velocity head, right, or kinetic head also you can say, there is no problem, right? So first of all I need to find out the v2, it's better for us, so we can apply the continuity equations, that continuity equation. Okay, so this is what we have, a continuity equation. You can say this is a1 v1 is equal to a2 v2. Simply we have to find out the v2, so what I'll do, that v2 is equal to a1 v1 by a2. Okay, now so then just hold on, where is that? Yes, so then we can say, we can change the page, right? So now you can say that v2 is equal to, directly I'm writing that v2 is equal to a1 v1 by a2, right? So a1 is nothing but you have a 0.0314 and the v1 is 4 meter per sec, right? 4 meter per sec by this is 0.00785. Am I right? Right. So this v2 is equal to, we have a 16 meter per second, that we got the velocity at the section 2. As you can see, the cross sectional area is very less, right? So the kinetic energy obviously it will be more, right? So now you need to find out the velocity head or kinetic head, you can say, that is velocity head at section 1 at section 1. All right, so velocity head at section 1 is nothing but that is v1 squared by 2g. So you can say v1 is what, that is 4 square by 2 into 9.81. so you got some values, that is this 0.815. these are the head, means we have to find out that distance only, right? So meter it is, right? Second, you can find out the velocity head at section 2 also. So this is what we have, a velocity head at section 2, right? So velocity head at section 2 is nothing but that is v2 squared by 2g. So this is what we have, a 16 squared by 2 into 9.81 which is 83.047 meter. All right, now then you need to find out the rate of flow or discharge. So you can say the rate of discharge, right? Or the q, simply you can say that q is equal to area into velocity. Either you can find at 2 or 1, no problem, right? So the same only, that continuity equation. So a1 v1 is equal to, this is 0.0314 into 4. So this is nothing but you have a 0.1256 meter cube per second, right? Or in liter cube per second you have to convert. So for converting this into liter per second, you need to multiply it with 1000, so it will become, that is 125.6 liter per second, right? So this is how we will apply the Bernoulli's equation, and how we derive the Bernoulli's equation, what are the assumption, and one working example we have seen, right? So we have some more typical problems, that applications also we have to learn the applications of Bernoulli's equation. So Bernoulli's equation application we are using in venturi meter, orifice meter, pitot tubes, and so on. So these things we will see in the subsequent classes. Thank you.